Namaskar students, in today's video we shall discuss a few more applications of Lagrange's mean value theorem. We shall see how Lagrange's mean value theorem can be used to prove some well-known properties of real functions. So let us start today's video. So this is our first problem. It says that if dash x equal to 0 in AB, then you have to prove that fx is constant in the closed interval AB. Now, f dash x equal to 0 means what? F dash x equal to 0 means the derivative of a function is 0 throughout the interval AB. Now, we all know when can the derivative of a particular function be equal to 0? Only when if the function is constant, because derivative of a constant is obviously equal to 0. So, the other way around you have to prove over here, it is given that the derivative is 0, then show that the function is constant in the interval AB. See how Lagrange's mean value theorem can be beautifully used to prove this result. So, fx equal to 0 in AB. Now, first let us consider, let x1, x2 be any two points belonging to AB, okay, such that x1 less than x2. So you are considering any two points from AB such that x1 is smaller than x2. So how will it look like? Therefore, the thing is that A, now the interval is A to B, that means A will be less than B or less, okay. So since x1 and x2 are from within AB, so you can write this x1 less than x2 less than B. So this is the sequence of the points that we had considered. A, which is less than x1, which is less than x2, which is less than the final point B. Now obviously, I have not given an equal to over here, so x1 is not equal to x2, and x1, x2 are any two arbitrary points. Now see, since f dash x equal to 0 in AB, so first of all, fx is continuous in this interval x1, x2. Now see, if the derivative of a function exists within AB, then the function is obviously continuous, because all differentiable functions are continuous, that we know about the property of a real function. So since f dash x exists in AB, so within AB you have x1 and x2, so f dash x will be existing within x1 and x2 also. Now since the derivative exists within x1 and x2, so the function will obviously be continuous within x1 and x2. Obviously, f dash x exists in x1, x2. Therefore, you can use Lagrange's mean value theorem to get a point C within x1 and x2 such that if x2 minus fx1 by x2 minus x1 equal to f dash c. That was a statement of Lagrange's mean value theorem. So since the function is continuous in x1 and x2 and the derivative exists in x1 and x2, so you can get a point C within x1 and x2 such that derivative of the function at that point will be equal to fx2 minus fx1 divided by x2 minus x1. That was a statement of Lagrange's mean value theorem. Now see, the beautiful part is that since f dash x equal to 0 in AB, throughout AB, now within AB you have x1 and x2, so the derivative of the function will be equal to 0 in x1 and x2 also, okay. Now what you can tell, see, since f dash x equal to 0 in AB, so you can tell f dash x equal to 0 in x1 and x2 also, because x1 and x2 is the interval which is taken from within the interval AB. Now see, where does this C point lie? C lies between x1 and x2. And we have found that the function's derivative is throughout 0 within x1 and x2. So this portion will also be 0 because C lies within x1 and x2. So in other way you can tell, therefore, if x2 minus fx1 divided by x2 minus x1 equal to 0, because the derivative of the function is equal to 0. Now what happens? See, fx2 minus fx1 divided by x2 minus x1 equal to 0. Now x1 and x2 are not equal points. x1 is less than x2, so they are not equal points. So how can this be equal to 0? Only when the numerator part is 0. So this implies f of x2 minus f of x1 equal to 0. f of x2 minus f of x1 equal to 0. Now difference of two functions is equal to 0 means what? fx2 equal to fx1. So you are finding that we have found that the function's value at a point x2 is equal to the function's value at a point x1. Now what are x2 and x1? x2 and x1 were some arbitrary points taken from within A and B. So this x1 and x2 can be any points from within AB. Now this is the twist in the tail. So for any two different points within AB, you are finding the functional value at those 2 points are always equal. So you take any 2 points and the value of the function at those 2 points are always equal. What does this suggest? That the functional value at all points within A and B are equal. So if the function's value at all points within A and B are equal, what can you say about the function? You can say the function produces a constant value, same value throughout all the points within AB. Now function producing same values throughout all the points within AB means the function is constant within the interval AB. This was what you had to prove. So if f dash x equal to 0 in AB, then prove that fx is constant within AB. That is what we had proved over here. Now this is another simple result of real functions that we need to prove. It is telling that if f dash x equal to g dash x in AB, that means if there are two functions whose derivative values are equal within the interval AB, then you have to show that the function, one of the functions, suppose fx is equal to the other function plus a constant within AB. That you have to prove. Now how will we prove this one? We shall use the Lagrange's mean value theorem and the previous result. Okay, the result of the previous problem, just the problem which we had done before this one, to prove this. See how beautifully we can prove this one. Let us consider the function phi x, which is equal to nothing but the difference of these two functions, fx and gx, within the interval AB. Okay. Now, if we do a derivative of this function f dash phi dash x, what we have equal to f dash x minus g dash x in AB. Now within AB, what do you have? F dash x equal to g dash x. So these two are equal. So you are subtracting two equal quantities. What do you get? 0. Therefore phi dash x equal to 0 in AB. Now derivative of the function is 0 within the interval AB. What did the previous result tell me? just the result which we had done before this problem. It tells that if the derivative of a function is 0 within an interval AB, then that function is constant within the interval AB. So, therefore, by Lagrange's mean value theorem, we can tell that the function phi x is constant in the interval AB. So, you can write phi x equal to some constant in AB, or what is the meaning of phi x? Phi x is fx minus gx, or fx minus gx equal to constant in AB, or in other words, fx equal to gx plus constant in AB. This is what we had to prove over here. This is the last result of today's video that we are going to discuss. If a function is differentiable in the interval AB, then you have to show that the function is increasing one if the derivative of the function is greater than 0, and the function is a decreasing one if the derivative of the function is less than 0. Now let us understand what is the meaning of increasing and decreasing. See, increasing means, suppose you have 2 points x1 and x2 where x1 is less than x2. Now anyhow, if you can show that this implies the functional value of x1 and x2 are also related in this manner, then you tell that the function is an increasing one. Means if the inputs are in increasing order, then the functional values also will be in increasing order. If this is the case, you tell that the function is an increasing function. If it is the other way around, suppose x1 is less than x2, but when you put a function upon x1 and x2, the inequality changes. If this is the case, then you call the function to be a decreasing one, because as you increase the values of the inputs x1 and x2, the functional value decreases. Here x1 is less than x2, but fx1 is becoming greater than x2. If this is the case, you call that function to be a decreasing function. Okay. Now over here you have to prove that fx is increasing if f dash x is greater than 0, and fx is decreasing if f dash x is less than 0. See, just to understand the increasing and decreasing function with examples, before starting the problem, let us first make it clear what are increasing and decreasing functions. Suppose fx equal to x square, and we all know that 1 is less than 2. So here see, f of 1, which is 1 square, is obviously less than f of 2, which is 4. So 1 is less than 4. So this is over here, this is an increasing function. Now if you try the other way around, suppose you have fx equal to 1 by x square. See, for 1 less than 2, here you have f of 1 is greater than f of 2, because f of 1 is 1 by 1, that is 1, and f of 2 means 1 by 4, which is less than 1. So over here see, the inequality changes. So this function is a decreasing one. To begin with this proof, let us consider 2 points x1 and x2 be 2 points such that a less than x1 less than x2 less than b. So you are considering x1 and x2 from within AB such that x1 is less than x2. Now when f is differentiable in AB, we always have, so the function f dash x also exists in x1 and x2. Since the function is differentiable within AB, AB is the bigger interval, and x1, x2 is the interval which is taken from within AB. So if the function is throughout differentiable within AB, the function will also be differentiable from within the portion x1 and x2 also. Now since the function's derivative exists, the function is always continuous. Because all differentiable functions are obviously continuous, real functions. Therefore, by Lagrange's mean value theorem, what you can say, if x2 minus fx1 by x2 minus x1 equal to f dash some point C, where C lies between x1 and x2. So the derivative of the function at a point C, where C lies between x1 and x2, equal to fx2 minus fx1 by x2 minus x1. That one, that's what the statement of Lagrange's mean value theorem tells us. Now consider these two cases one by one. The first case, if the function derivative is greater than 0, case 1, if f dash x greater than 0, so f dash C also will be greater than 0. So what you have then, f of x2 minus f of x1 by x2 minus x1 greater than 0. Now see, from here you can tell, which implies x2 and x1 are two different points, not equal, where x1 is less than x2. Keep this in mind, x1 is always less than x2, that is what we had considered. Now from here what you get, f of x2 minus f of x1 greater than 0, which again implies f of x2 is greater than f of x1. Or in other words, you can tell f of x1 is less than f of x2. So what you are getting, let us simplify it. See, therefore, what we are getting, we had considered x1 less than x2, that implied f of x1 less than f of x2. So when you have an increasing sequence of numbers where x1 is less than x2, you are getting the same increasing sequence of the function where f of x1 is less than f of x2. Hence, by the definition of increasing or decreasing functions, you can tell here f is an increasing function. Now for the other case around, what happens if f dash x is less than 0? See over here, for the second case, case 2, if f dash x is less than 0, then this one will be less than 0. Similarly, this will be less than 0, this will be less than, and obviously you can tell that means what, fx1 is greater than f of x2. So in other way around, you are getting when x1 is less than x2, f of x1 is becoming greater than f of x2. So when x2 is greater than x1, you are getting the reverse thing, x2 is decreasing when you are putting the function upon it. Okay, so when x1 less than x2, you are getting f of x1 greater than f of x2. Now this is the definition of a decreasing function, because as the sequence of numbers are increasing, the functional values are decreasing. So you can tell for f dash x less than 0, the function is decreasing. So my dear students, this is all what we had for today. If you have understood today's video, the problems discussed in today's video, do share this video with your friends like my video, follow my page, and don't forget to subscribe to my channel. Till then, goodbye.